Okay, welcome all of you to the third lecture in this classical mechanics 1 course. So today lecture 3 will continue with the Newtonian mechanics. Then we'll discuss about degrees of freedom. Generally, I will denote with the DOF, and constraints. But before that, let me recap of the last 2 lectures. Okay. So, in lecture 1 we had the plan of this course. We discuss about the syllabus, we discuss about the study material, books, we discuss about the plan, etc. And in the second lecture we started with the Newtonian mechanics. So, we discuss Newton's laws, particularly particular emphasis to the first law, and also we discuss how we can calculate a classical system, or how we can understand a classical system by calculating force on individual particles. And there was some disturbance in last lecture, technical disturbance, so we could not discuss complete well. So, let us start with the things where we ended last time, that how one can calculate or know about a classical system by using Newton's law. So, as I already mentioned that one need to calculate the force on individual particles. So, suppose you have a system of n particle, suppose particles. So, we denoted with the number I, and then we need to calculate the forces on each and every particle. So, the force on the ith particle can be written by the rate of change of moment of the ith particle, which will be equal to the external force acting on the ith particle, plus there will be some mutual interaction between the particles. So, we will have the force due to all other particles acting on the ith particle. So, let us denote it with that F I j, where j goes from 1 to n and j not equal to I. Okay. So, this is your internal force and this is your external force. So, in Newtonian mechanics, what you have to do, you have to calculate the forces for all particles. So, that you know how to isolate these particles by drawing free body diagram and then calculate. Then these are generally a second order differential equation. So, these equations are generally which you need to solve. This, if it is analytically you can solve, then it's fine, otherwise you can take help of computer to find the solution, and the solution will give you the position of the classical system in all time. So, this is the main purpose of a classical system, that you should know the position, how it changes with time. So, you can solve this by using Newton's law. and if there is symmetries, let me talk about symmetries. It will help you to find the solutions. So you can take help of symmetries. So let me talk about certain symmetries. Later we'll show that symmetries, when what does symmetry means? If the system remains invariant under, suppose, the rotation of coordinates, or the system is invariant under, say, translation in time or translation in space or any other symmetry, continuous symmetry, then symmetries implies conservation laws. So later we will see that will prove for certain symmetries that how it leads to conservation laws, but we already familiar with certain symmetries, and if you have certain quantity is conserved or does not change with time, then it will help to find you the solution of classical system. How? Because you know certain quantity does not change on time, so you don't need to find how it behaves with time. So if you have a conserved quantity, or if you have certain quantity doesn't change with time, then you know that you don't need to know that quantity for all time. Okay, so this helps. You don't need to solve equation for that quantity. Okay, so there are many symmetries. I give you some example. For example, if you have translation in space, that will lead to the linear momentum conservation of linear momentum. This related to a symmetry we'll see with that translation in space. Suppose r prime equal to or shift of origin. Now this leads to the thing that the external force will be 0. So if you have a linear momentum conservation, then you will have the external force of the system equal to 0. Similarly, if you have rotational invariant, so rotational invariant will implies conservation of angular momentum, and the consequence of it is that the torque acting on that will be 0. So torque acting on this will be 0. So this will help you to find the solution of the classical equation. Similarly, the time translation goes to the conservation of energy. Conservation of energy, which has a consequence that curl of the force will be 0. Okay. So these symmetries and their consequences. So conclusion of this part is that symmetry of the will have some consequences on the forces or torque, and that can be used to find, that can help to find the solution. So symmetries of the classical system will help to find the solutions. Now this is all about that Newtonian mechanics, and now we'll see what are the problems associated with this Newtonian mechanics. So first problem, let me list down problems in Newtonian mechanics. Okay. So first we'll see, we already mentioned when discussing the first law, Newton's laws, the laws valid only in the inertial frame. So certainly question is that this is of course a disadvantage, and question of course is that why there is a preferred system. So more philosophical question, why there is a preferred system. So in last class I forgot to explicitly define the frame, so let me define. So what is inertial frame? So inertial frame I can define with that is of course a relative concept, and you can define inertial frame that if a frame is absolutely at rest, is not moving, then we can consider as an inertial frame. But everything is moving in this earth itself is moving, so it cannot be an inertial frame in that sense. Earth is rotating, it's moving. So to define inertial frame we need two frames. So if we have a frame which with respect to another frame is at rest or moving with a uniform velocity, then we call the second frame is the inertial frame with respect to first one, or vice versa. So inertial frame, so let me write down, is rest with respect to another frame. So you have two frame if they are mutually at rest, or one frame is moving in a, or one is moving with other with respect to constant speed. Okay. So they are called inertial to each other, and Newton's law has to be valid only in the inertial frame. That is the biggest disadvantage of this. You cannot write, I'll explain this with respect to more details, but before that let me in this context say about the non-inertial frame also. So as example, so for example, if you have a frame, say S prime, moving not in a constant speed but moving with acceleration, with respect to S, then this is called the non-inertial frame. Similarly, if you have a frame which is rotating frame is also non-inertial frame. The characteristic of non-inertial frame is that you will have additional forces will appear in these frames which are called the pseudo forces. So the characteristic of this, so all you have the pseudo forces appears in the non-inertial frame. Okay. So now come back to the inertial frame. I said that Newton's laws, the biggest disadvantage of Newton's law is that it has the non-inertial, it has to be valid in the inertial frame, and it is inertial frames are the Cartesian coordinates are chosen for the inertial frame. So I'll explain this a little bit more. Suppose you have a spherical coordinate system, and then this equation, if we write Newton's law, then this will be the equation, right? So which cannot be true. So Newton's law cannot be true in this frame, because if this is true, if this is true, then a planet cannot move in a circular orbit, never can move in circular orbit, because if for Fr not equal to 0, R double dot will be not equal to 0, and R dot will be certainly will not equal to 0. So it cannot move in the so Newton's law, in other words, is only valid in the Cartesian coordinates, in the inertial frame, which we generally take as the Cartesian coordinates. So this is the biggest disadvantage of Newtonian mechanics. So, and the second one, the second disadvantage is that the dynamical problems are always always in terms of forces. So which is a forces, which is a vector, and you have to pay additional attention for each and every particle. This forces, which is a vector, so it has magnitude as well as it has direction. So it is kind of this implies that discussing a system of particle, keeping track of the forces on each and every particle is very cumbersome. Very cumbersome. So we have two problems, Newtonian mechanics. One is that you have to use the inertial frame, which generally people consider as the Cartesian coordinates. And the second problem is that dynamical problems are always in terms of forces. That equation of motion we write always in forces, which is a vector. So for each and every particle you have to keep track of this, and if you have large number of particles or many particles, then this method is very cumbersome. And this implies the need of, alternative formulation of classical mechanics, which will be the subject of this course. Okay, so this is all about Newtonian mechanics. So let me ask a activity question, that in which way, what are the disadvantages of Newtonian mechanics, and which way we can remove this disadvantage. Okay. So let me briefly summarize little bit about this, that we know that a classical system can be solved or can be studied through Newton's laws of motion, and in that you have to solve the forces, you have to find the forces for all particles individually, and then you have to find the solution. It is basically the solving a second order differential equation, whether you can solve analytically exactly, or you can take a computer's help to find a approximate solution, and for all time you find the position of the classical system. So this is the Newtonian mechanics, which you have learned in your Mechanics 1 course, and we find there are certain disadvantage of this mechanics, and we will be going to learn a new formulation which will be the topic of this course. So let us start this, and to start this we will start with this concept of degrees of freedom. For this course I will always denote degrees of freedom is DOF for henceforth. So please pay attention to this, and also I want to remind you the concept of point particle. See, I already defined a particle is called point particle if its own dimension can be neglected in describing the motion. So concept of point particle is a very relative concept, and depending on the situation, some particle can be considered as point particle, same particle cannot be considered as point particle. I gave the example that Earth, when moving around the Sun, the distance between Earth and Sun is very large. In that case, Earth's dimension can be neglected and Earth can be considered as a point particle. But when you consider the rotation of Earth about its own axis, then Earth's diameter is important in that case. So you have to consider the moment of inertia calculation, and you have to consider the Earth diameter. So Earth, while describing its motion around the Sun, is a point particle, and when describing Earth's rotation, it is not a point particle. So point particle concept is very relative. But in this course, whenever we will say a particle, always this will mean a point particle. The extended particle, which is the one example is the rigid body. So, is another concept will be used in this course. Rigid body, which is the collection of particles or point particles. Okay. So, these two in this course will be used, particle and rigid body. Particle, by particle we always mean that it is a point particle, and rigid body will be collection of point particle under certain condition which we will define later. So, with this, now let us move to the concept of degrees of freedom that we said. So, degrees of freedom, how we will define that? So, number of independent variables require to specify the position of a classical system at a particular instant of time. So, this is the definition of degrees of freedom we will follow in this course. The number of independent variables required to specify the position of a classical system at a particular instant of time. If we consider few examples, this will be clear to you. Suppose some incident happened. So, you want to specify the position of the incident, and in 3-dimensional space you need 3 variables: how far it is along x direction, how far along y direction, and how far in the z direction. So, you need 3 variables corresponding to x, y, z to specify that position of the event. Suppose some accident happens somewhere. So, where it happens, you from this place, this classroom, you can specify by giving 3 numbers. So, that will be the degrees of freedom for that system will be 3. Okay. So, but important thing is that number of independent variables and also particular instant of time. So, this you have to so in one particular of time, what will be the variables required to specify this. So, let me consider few example, and let us consider first free motion. One particle in one dimension. So, its degrees of freedom will be certainly will be 1, because it is moving along x direction only, one dimension, or y direction. So, you need the value of the x coordinate. So, it will degrees of freedom will be, and say you can say that value of x will give you the degrees of freedom. So, suppose one particle moves on a plane. So, plane is 2-dimensional, you need to specify x and y. So, degrees of freedom certainly will be in this case will be 2. So, suppose now you can consider if one particle moves on a 3-dimensional space, 3D space, 3-dimensional space, certainly its degrees of freedom will be 3. So, similarly, if you have a particle in n-dimensional, particle moves on a n-dimensional space, its degrees of freedom will be n. So, if you have m number of particles, in n dimension, then degrees of freedom will be for each particle n degrees of freedom. So, m particle degrees of freedom will be in m. Okay. So this will be the this all we consider in free. So now degrees of freedom. So in this context, just let me repeat what we said. So if you have free motion, then the degrees of freedom will be same as the dimensionality. If and degrees of freedom will be added up for many particles. So if you have 10 particles on a plane, so plane means 2 dimension, all 10 particles are free, then degrees of freedom will be 10 into 2, 20. So let me conclude this lecture by saying that we have learned how to calculate the position of a classical system in this lecture, and then we find that what are the difficulties, because when you calculate the forces by using Newton's law, you have to, there are certain difficulties. I said that was the disadvantage of Newtonian mechanics. One disadvantage is that it always assumes an inertial frame. Second disadvantage is that the dynamical problems are always in terms of force, which is a vector quantity. So if you have many particles, you will have many vectors. You have to keep track of all vectors, magnitude and time. So now in the next class, we will see that if there is a restriction, so far we consider only the free motion. Now if there is a restriction, because all motion is not free, there are a lot of restriction, and if there is a restriction, then what will be the degrees of freedom? So those restrictions are called constraints. So in next class we will discuss the constraints and how it will reduce the degrees of freedom of a system. How these constraints can be dealt with will be the topic of next class. Okay, thank you.